Hello and welcome to another episode of Post Cloud, where we talk about all things cloud technologies, cloud futures, what new technology a salesperson is trying to ram down your throat this week. My name is Chris Krantz. I've been a cloud guy for over 10 years now. I love cloud technologies. More recently, been getting into cloud native tech and serverless technologies and those sort of things. As always, accompanied by my lovely co-host, Stephen.
Thanks, Chris. Hello there. I'm Stephen Howell. I'm an infrastructure guy mainly, although recently I've been lured over to the dark side by the lure of infrastructure as code and programming, and specifically the likes of Kubernetes, which has made that much more extensible. This week, we are going to be looking at something that follows on a bit from last week, aren't we, Chris?
Yeah, absolutely. So last week we were talking about IOPS and storage requirements, which invariably is led by a conversation about databases. And one of the things we touched on previously was some of the decisions you can make around those database architectures. So Stephen and I thought it would be great to talk about databases, data architectures, and so on. And primarily is going to be the difference between your traditional RDBMS, SQL style databases, or the more modern cloud native, you might call it, NoSQL. As we all know, this is cloud days these days. So everyone's in the cloud, whether that's private cloud where you're doing the same thing but wrapping the word cloud around it, or we're in public cloud where you're saying paying someone lots of money to run their computers for you. It encourages us to rethink the way we're doing databases. Databases are the core part of almost every application. At some point, you've got data persistence, we talked about last time, and you need a way of actually referencing that and actually having that the user information. Because after all, if users are using a system for a reason and there's data behind that, that's where databases come in. So, Stephen, we were talking before about IOPS and the different ways of scaling that. The obvious way that we've done things traditionally is just scaling up.
Well, no, of course, that's not the reality. That's a laughable fallacy. Instead, you've got to come up with a real solution that meets real demands. It means making do with a lot of commodity nodes and accepting certain realities like failure, component wear. We've got a whole raft of different solutions that focus on different strengths and weaknesses and reflect varying priorities throughout this spectrum of data storage, if you will. We can think of the world of databases as a spectrum of data storage. And it's maybe not even a spectrum between 2 points. It's more like a color wheel between several different factors.
But what is the problem we're trying to solve? I mean, SQL seems like it's a structured query language, so it's very, very relational database, very, very structured in the way data is laid out.
Where you run into difficulty is if you decide you've got rows and columns that are linked to each other in unexpected ways. That gets difficult to navigate. And so the limitations that informs the style of data structure of the tabular traditional database do not exist in modern computer systems. They've got plenty of storage ability to store images and to store videos. They've got computational and working memory enough to do complex relationships between entities and to be able to store multiple revisions of the data. And so this has informed the creation of a new set of data structures that allow this type of storage. And Chris, I think this might be your kind of more your side of the fence, the distinctions between these various types. Do you want to tell people a little about that?
But first and foremost, I want to highlight one thing. When I first saw the term NoSQL and started to hear people talk about it, the automatic assumption that came to mind was no SQL, as in this is not. We're going to get rid of all SQL. We're going to get rid of SQL totally. And the reality is that the no part of it there is not only. So most of these platforms actually do very similar things. They can be highly relational. They can be highly consistent. They can do all the things your traditional SQL databases did, with a few exceptions. But they're just designed to do it for a very specific type of data set, which we'll get onto now. The first one is probably the one you've heard of most, which is the document store. This is where you're storing documents. A lot of the time they tend to be JSON documents, so they're still highly indexed, very, very easy to search and categorize, but they're designed specifically for this purpose. Next one is, again, one you've probably heard of, is the key value store, popularized with Redis I know Redis typically we see as a cache, but really what you're doing there is kind of a key value cache. So you're caching, you're giving high performance database storage to things like session data or really simple data that just needs a key and a value. You want that to persist, maybe be available across a couple of different applications, but you want something that's very high performance in doing so. The next one, which is probably you may come across less, but you've probably used it, is the graph database. This is the sort of database that's designed to really bring together relationship models. So no surprise that social networks, really this is where the graph database came from, was building out these social networks. Being able to find one person, it's kind of like the 7 degrees of Kevin Bacon. You can link 7 different people and you'll always get back to Kevin Bacon, I think is the story, as the story goes. But you've always got this connection. I'm sure folks on LinkedIn, most people are usually a third connection, and that's because you create these complex graphs of how people are interconnected. It can also be great for things like recommendations engine and fraud detection. Again, we've got these complex data sets that have similarities and links, but what you need to be able to do is very rapidly detect what those relationships are, which traditional databases couldn't do it. Document stores really aren't designed for doing that. Not really complex, kind of think about the width you might go through for that complex relationships. Another one we've seen bloom kind of in popularity over the past 5 to 10 years is the time series database. With the growth of things like Prometheus for monitoring in Kubernetes and nowadays cloud as well, the time series database is there to literally, it stores data in a time series. When I'm looking at things like monitoring data, what I want to do is go back and look at it in a time-stamped manner. I want to see, okay, give me a sample of things over the past hour, or wind back a week and give me 4 hours on Monday. Those sort of things is what time series is really, really good at. You've also got column databases and then other database types. Each of those has a different use case. And I think this is one of the important takeaways for me is you're looking at these systems and you're not necessarily going to be using one tool to do everything. There are some interesting technologies out there, some interesting database vendors out there creating these sort of multi-purpose, I think they call them database polyglots, where you can actually choose the data architecture of the different data structures. But generally, you're going to be choosing best of breed. I want a session store, I'm going to be choosing Redis. I want a time series data, I'm going to be choosing Influx or Prometheus or something like that. One of the things you're generally doing with all these systems, though, one of the things that's a general rule across all these NoSQL systems is they take that monolithic paradigm that we had with the RDBS and throws that out the window and says, what we need is a scale-out system. If I start with 1, I want to be able to, at some point in the future, have 1,000. And I don't want to have to compromise on growing from 1 to 1,000. You've got these cloud economies of scale where I start small and grow with my user base. So what we're doing with that is we start growing out the way we're spreading that data out and scaling things out in a very horizontal way. It also allows you to be very efficient with those building blocks. Those building blocks can be quite small. Now, there's part of your architecture decision is going to be, do I go with large nodes or small nodes? There is inherent overheads in having lots of small nodes versus lots of large nodes, but the initial price of doing the smaller nodes is obviously going to be cheaper. We're not going to get into the details of that today because that could probably be an entire episode. One thing I did want to talk about, though, was one of the things that I, again, came up with when we first started talking NoSQL databases from the SQL team was the concept of consistency versus eventual consistency. What you're saying is that when I'm writing my data, it's not necessarily copied to all the places that it should be. Now, if you think about that traditional database, when I write my data, it's going to one place, that one big monolithic database. That's really easy for it to turn around and say, yeah, I've written the data, you're good to go. In a scale-out system, when I'm writing my data, I need to know how many copies of that data is written. And so that's where you might come into this idea of eventual consistency. You can still get a guarantee that the data is safe, but that data may not be consistent, as in copied across all those nodes, or all the nodes that it should be copied across. Most of these systems allow you to choose that order. So it's not like, oh, I'm choosing an eventual consistency, I'm going to start getting stale reads. That's not the case. You get into something we'll come on to a little bit later on when you're making these decisions. Another famous story was, I think it was when the PlayStation 4 went on sale a few years ago. When you went online to purchase the PlayStation 4, everyone got a success or got a message to say, yep, we've got your order, thanks for that. And then a large number of those users got an email the next day to say, sorry, we ran out of stock. We can't fulfill your order. You were on the wait list. And this is the idea of actually your shopping experience now is also eventually consistent. Some people may have been in that situation where you've actually to say, I'm taking your order, but I'm not fulfilling it. You will see this happen at Black Friday occasionally. Some organizations, some retail organizations take the view that no, we're not going to do that. And again, you get this weird user experience where on Black Friday, you're actually in a shopping queue on a website. You're in, your queue number 9 out of 500. It's a very, very strange thing to experience online, but that's the way they're going to say, I'm going to give you guaranteed consistency of your transaction. But in order to do that, I'm going to have to put you in a queue.
Right. So we've just looked at consistency, eventual consistency, and that's part of the kind of backing theory behind databases, right? What do you want consistency to be? You also have, what do you want availability to be? What do you want your partitioning behavior to be? And these kind of questions, they push us down a couple of different paths. And traditionally, it pushed us down a path towards something that was called an ACID database, ACID being a moniker that stands for uh, atomicity, consistency, isolation, and durability, which means that operations are atomic and that a single update to the database is completed as one operation and it doesn't influence operations around it. It can happen independently of anything else. Consistency. The data moves from one consistent state to another consistent state. It's never in an in-between state. Isolation. The view of the data that you have at any one time is valid during transactions, I guess would be the best way to put it. And durability, which is like crash consistency, that if there's a failure at any time, the database can always record the current state. Nothing is kept off disk. Everything is always written to disk, such that a transaction is only fully completed after the disk has been updated and an OK response is returned. That gives us a system that focuses very much on returning the correct data in the correct order and ensuring that if two people look at the database at the same time, that they're always going to see the same response. The way that things have gone in modern times, I guess we could say, would be towards a modern invention of that, which is base, that it's basically consistent. This basically speaks to what Chris was saying of eventual consistency. You've got the ability for different users to maybe get different views of the same data, that the spirit of the data is such that the system will eventually converge on values, not atomically step between the current state and the next state. It will sort of eventually move towards the state that it should occupy. And this means that the system is much more tolerant of things like running at scale. You can scale these horizontally. You can put the system across multiple nodes because that convergence will happen across the network. The updates will flood across the network over time, and the systems will eventually harmonize on the same value. It's much better if you've got lots of people simultaneously accessing the system. Whereas an ACID database is inherently transaction limited, you're going to have trouble serving more than a certain number of queries. Whereas if you go for a distributed base system, you can simply add more nodes in to provide you with more query capacity. And again, you've got convergence to eventually shepherd the overall data in the right direction. This also depends greatly on the type of data that you want to store. Because you've got so much more space, generally speaking, in a scale out distributed system that might have base characteristics rather than ACID characteristics, what you tend to have is much larger sets of records. The sets of records are millions upon millions of entries. They may be even too large for a single system on the network to be able to put into their working memory. And that means that what you used to do with a relational database, where you'd take one table and you'd say, look at this one field on this table, and then I want you to match this table to all the entries that have the same field in a different table and join those up for me. That's called a join operation. Whereas that is the core of what relational databases do. It's their reason for existing, in effect. When we move on to NoSQL systems, that's discouraged at best, and at worst might be physically impossible for the data set. You might have to schedule large, say, map reduce operations that happen out of hours to go through and do specific operations on your data set. But doing on-demand joins for a single person accessing the data set is generally unfeasible. And that reflects the type of data that you can store in each of them. If you've got this traditional relational data, which is relational, it's got a whole bunch of different tables, and all those different tables have key fields that link to each other. Maybe there's a national insurance number in one field that links from a person over to their tax records in another field with their national insurance number there, something like that. And then we've got to do additional lookups to find where they live, to find what their company is, and so on and so forth. That can be done in a relational database relatively easily. But if we want to try and do the same thing on demand in a NoSQL store, we can find ourselves looking at an impossible to manage mountain of data, and coming to the conclusion that what we're going to have to do is to schedule an operation out of hours that won't just return the data on demand, but will create an entirely new table or storage area in our data system to house that data. And that, I think, comes down to some of people's expectations. Like you say, information architecture, a lot of people assume they can take data from a relational database and they can just pop it into a NoSQL store. And they can benefit from increased availability, increased partition tolerance, and so forth, right? But that's just not feasible all the time. You need to actually think about information architecture, like you were saying there, Chris, that you can't just forklift stuff. And this is, again, a running theme. You can't just take the old stuff and pop it onto new infrastructure and expect it to suddenly be new. That's not how digital transformation works. If digital transformation is to be effective, then it has to consider what the original problem was and solve that problem again with new equipment and new tools, not just pick up the code that you wrote 20 years ago and go, throw it over the wall. There we are, new system. Woo! There's no free lunch there.
And as you say, I think that's an ongoing theme, is take this in a view of continual improvement. And you're going to be looking at this, and you're not going to replace your SQL Server overnight. I would recommend you don't. And it may be that you never replace your SQL Server. The whole concept of NoSQL and document stores and key value stores and all the rest of them is that they augment your data stores, and you start moving different data sets that are fit for purpose in these different systems into what they are. Also, you don't want to end up with 10 different flavors of database just because you've got 10 different core data types. That's a lot to manage. If you're a large multinational finance organization, fine. If you're a government, fine. Most people aren't those things. And so having 2 to 3 database systems is probably about as much as you want to do. So with all these things in scale out, NoSQL architecture and the rest of it, what we often come across, and what you may have seen at some point, is the concept of CAP theorem. You may have also heard it called Brewer's theorem. This also gets expanded into a couple of other theorems that we'll talk about a little bit. But CAP theorem is, if you think about having a triangle, you've got consistency, availability, and partitioning. But you can only choose 2 of those things. So if you think about consistency, right? So if I'm choosing consistency, what I'm saying there is that when I make a write, I want every single node in my cluster to agree that that write was made before I come back and say to the user, yep, your write was made. Now, that is challenged by partitioning. So if I make it a write that's across a geographical area, and my cluster gets partitioned, as in I lose access to certain nodes in the cluster, my partitioning comes in play there, and it means I can't guarantee my consistency. Now, if I'm saying my consistency is absolutely key, the solution there is to say that in the event of a partition, I'm going to start erroring writes. And that's where you then turn around and say, well, actually, I don't want to error write. I want something that's highly available. So in the event of a partition, I want something that's still available. So I'm going to compromise to some extent my consistency by saying I no longer need every single node in the cluster to agree to the consistency. I need the majority, or you might say quorum, of nodes in the cluster to agree to the consistency. And that's where you start balancing these different things. And this is where you need to go into it thinking, okay, what is my objectives here? Do I want something that's very, very partition tolerance? I can lose an entire continent and things are still available to my users. Things are still in a consistent pattern. Is things available? So when things do go wrong, do I still have read and write access? Read access is actually relatively simple. Write access is a lot more complicated. Or do I have consistency? Do I want to guarantee those that my rights are the same rights across the world? Cap theorem to some extent gets extended with kind of the else side of things. So if I've got consistency, availability, or partitioning, if something fails, then what am I going to compromise? And generally, you're then saying, okay, I'm going to compromise latency. So that's the amount of time it takes to read or write my data from the system, or I'm going to compromise my consistency, i.e., I'm going to make a write and I'm going to say you will eventually be available on all those nodes, but I'm going to confirm to my user that at least X number of nodes have confirmed that right. So we're scratching the surface there. I'm sure some people will be upset that we've said something wrong or not said something in enough detail, but we kind of want to give you an overview, a decent overview of all the elements of NoSQL without jumping too far into all the details.
There's a psychological aversion to picking anything that might not be consistent. And I've seen people say, oh, we can't have an inconsistent state for our system because they assume that if there's no consistency guaranteed 100% of the time, that 100% of the time the system will be effectively in error. And that's not really the case. You're merely saying that writes might be delayed. And when you look at it, the things that happened this second, they might be arriving in 5 seconds' time. It doesn't mean that you're looking at data that's wrong. You're just looking at data that might be slightly historic compared to the exact current state of the rest of the system.
That is really useful in many, many scenarios. So when people say to you, "Oh, I'm not sure about eventual consistency. I'm not sure about using that system," make sure you're looking at the data, and if that data actually needs to be fully consistent to every person's view of the world. Now, the other thing on that is a lot of NoSQL systems are fully consistent. It's actually there's quite a few levers you need to pull and settings you need to change to make them eventually consistent. So you have this architectural decision to make as to am I doing this consistency. So you have this, like Stephen says, you have this psychological pushback on, oh, we're not looking at NoSQL. That's that inconsistency stuff, which is making that incorrect assumption that we're not talking about eventual consistency. And actually, most NoSQL systems aren't eventually consistent anyway.
Do you have any little examples? I'm thinking we could close this out by mentioning some of the technologies and some example applications that are well suited to them.
So there are a few times where you might want to choose certain data architectures and data technologies depending on your use case. I think one of the obvious ones earlier was Redis. We covered this earlier. There's a few other different technologies similar to Redis, which give you either that kind of in-memory cache, or just what you're generally doing is caching from a key value perspective. You're caching certain queries that need to have that rapid response. And I think if anyone's got some sort of system where you've got some level of control over the data architecture, having that a Redis cluster in line makes a lot of sense. You're just going to be accelerating a lot of those frequently queried sets of data. For other key value stores, you've got popular ones like DynamoDB, for example, is again very, very rapid access, very, very fast. The use cases there, you need to be able to know the data is. One of the quirks I've had in the past of playing with DynamoDB. Some people who have used DynamoDB and similar, no doubt, laugh at me. Coming from traditional kind of MySQL, I used to be a MySQL DBA and developer. I was thinking, okay, I could just move things across into DynamoDB and have a similar look and feel. Okay, it's a key value store, sure, but surely I can do similar operations, such as I want to choose a random record. No, you can't do that. You don't have these inherent kind of built-in queries. You're going to be pulling down a full table, then using your front end or maybe your back end code to query through all those records to select a random record in order to do that. So there's certain things that you can and can't do with these different systems, and it's important to understand those before jumping in to say, well, DynamoDB is really fast, it's very scalable, and it's very, very cheap. We should use that for everything. That would probably be a bad idea. These are decisions you make based on your data architecture, especially with this idea of the rapid release, going for the MVP, and just continuous improvement. You start with the MVP, so the minimum viable product. You start with what it needs to be. You can put some thought into what the future is going to look like, but you don't need to make that decision yet. And I think that's really the power of NoSQL systems is it gives you that ability to do rapid prototyping, to do rapid evolution as well.
I've seen some areas where you've got, say, streaming data, you've got a monitoring system that's kicking out a whole load of data into a streaming platform like Kafka, where everything has implicit ordering. And if you've got a series of monitoring data where you're always viewing it in a chronological order anyway, then that kind of fits nicely into your information architecture.
I think that Kafka architecture fits in quite well to the eventual consistency we were talking about before. A lot of the time, you'll be taking Kafka as a stream, and then you'll be processing it, and so you get that view that I can receive all this data. The view of that data might be delayed.
So let's sum this up. I think we've seen a mindset shift. We've seen people grow up in a world of enterprise, singular solutions, very expensive servers, budgets that encourage them to spend more and more on single nodes of hardware to make them faster and more powerful and more resilient. And then that slowly be eroded by a movement to cloud where raw numbers of nodes ruled. And when you give people raw numbers of nodes, you encourage very different approaches to those problems. So we've seen people favor less the extremely large boxes and more the extremely large numbers of boxes because that was easier to manage and it appealed to applications with global reach. There's been some interesting talk about availability and consistency in there as well and what that actually means to you. And I think we're going to look more in the future at what data protection and data resiliency has to do with that. We've also learned a few things about attitudes to data. So, what do you think's changing in the attitude to data?
You pretty well summed up in that mindset shift between that traditional enterprise view that my data needs to be absolutely consistent and available everywhere, and you want all the things all at once, to that kind of the cloud native type mindset where you pick and choose your data architecture that fit for purpose. When you have that enterprise view, that enterprise mindset of your data, you look at, okay, what is my data going to be in 3 years' time? I need to know that. If you don't tell me that, I can't build you a system. Versus that more modern kind of cloud native approach of tell me the type of data and the style of access pattern you're going to have, and I'll build you a system that can scale, regardless of how you want to scale that too. We could be successful, we could IPO, we could be a flop, but I want to build an architecture that doesn't cost the earth and will scale with our customer demand and income demand. So my summary really is don't be scared of NoSQL. Don't get caught up in some of the misguided preconceptions of what it is. NoSQL is not no SQL. It is not only SQL. So it's something that's going to augment your existing databases, your existing data models, your existing data architecture for benefit of everyone. You're going to build a system that can scale out. Don't go in this blind to CAP theorem. Do your own research in it. Definitely study it. Look at, okay, what are the different levers I need to pull? What happens in these different failure scenarios? We've talked about this, and I think we're going to conclude pretty much every episode with test it. Go and pull the plug a few times and see what happens. See what happens to the user responses, what happens to your data. It's a really important part of all this model. We're talking cloud, and cloud needs to be resilient. You've got cloud resilience. Even Amazon don't get it right. The number of times that we say, things have gone down because US East 1 is offline.
Well, I'm very much in favor of testing it. I'd say if you're going to build something, make sure you automate it as well so that it's easy to stand up. And if the worst happens, then you've got a nice easy button to push and restore your data and flip things back to the last time that you did a data backup of some sort. But yeah, really knowing the right tool for the right job. It's a good mantra. There's lots of different types of data. There's lots of different types of data storage problem. And there's lots of different types of business need. And you have to look at a combination of those to figure out where you're going to sit.
Thank you very much, and I hope you enjoyed the show. Don't forget to like and subscribe and all those things you do wherever you're viewing us. If you're listening to us on podcast somewhere, don't forget to subscribe. If you're watching us on YouTube or seeing clips on LinkedIn, then again, welcome to you, and I hope you're enjoying the show.
Likewise, if you've got any questions, please drop a comment on YouTube and we'll see if we can include it in future shows. Bye.
Bye.